So now we want to broaden our horizons just a little bit, and the first thing we're going to do to broaden our horizons is shrink them. So let's define a class of problems that make it much simpler to ask these fundamental questions. And the class of problems is called the class of decision problems. So here's my definition of a decision problem. A decision problem is a problem that has a yes or a no answer. Okay, any problem that if I give you an instance of the problem, that instance either is yes or is no. All right, and I'll give you an example in just a second here. So decision problem, either yes or no answer. Okay, so here's an example of a decision problem, and let me just call this prob 1, just for the sake of giving it a name. So prob 1 says, given an array and a threshold, does the array contain an element that is greater than or equal to that threshold? Okay, so it's a simple problem. So given array A, and we'll say this goes up to n-1, and threshold m, and we'll just say the m is greater than or equal to 0, because why not? Does A contain an element I such that AI is greater than or equal to M? Okay, simple yes or no question, right? Either it does or it doesn't, right? There's no ambiguity. There's no way that we could be like, I don't actually, there is no answer to this question, right? If I give you an array of numbers and a number, you can check to see if there's an element in that array greater than or equal to that number, right? Done. Okay, so here's an example of a decision problem. Most of the decision problems we're going to look at in this class are going to be more complicated than this, right? They're going to be variations of things like the knapsack problem. But this is a nice simple toy example that we can start out with. All right, so now this is our definition number 1. So from here on, at least from here for a little while, for at least two sets of videos, every problem that we look at, we're going to assume is a decision problem. Okay, so and whenever I define new classes of problems, they're always going to be subsets of the class of all decision problems. So there's not going to be any optimization problems for a bit, right? For at least two lectures coming up. All right, so decision problems, the reason we like decision problems is that they give us a really simple set of tools for analysis, right? You can say, if I give you an instance of a problem, you can say this is a yes instance or this is a no instance. So for example, with prob 1, here's an instance of problem 1 right? How do I specify an instance of problem 1? Well, I give you an array and I give you a threshold. Right, so here's my array. A is 0, 5, and 7. Right, it's a short array, but it's an array. And my threshold is 6. Okay, and so we can identify whether or not this is a yes instance or a no instance, right, by looking at what question the problem is asking. So the problem is asking, does the array contain something bigger than or equal to the threshold m? And sure enough, this does, right? So this is a yes instance. And we can identify this instance as a yes instance. The threshold is 6, and sure enough, there's something that's bigger than or equal to 6. Okay? And just in the same way, we can identify a no instance, right? So here's another instance of problem 1. Okay, where our array is just going to be an empty array. Okay? And then the threshold is going to be the same. Threshold will be 6, right? Is this a yes instance or a no instance? Well, this is a no instance because there is nothing there is no index that we can look up in A that gives us a number that's greater than 6, right? So this is a no instance. So no matter what I do, no matter what I write down, I can always identify whether the instance of the problem is a yes instance or a no instance. Okay. So one of the crucial questions in CS theory is this. Given a problem, how fast can I determine whether it is a yes instance or a no instance? And so what we do in algorithms and in CS theory generally is we break up the class of decision problems into these subclasses that are all arranged based on how fast we can identify the answer. So one of the most important classes of problems is called P. P stands for polynomial, and it's defined like this. And there's various definitions. This is not the most formal definition. Hopefully in Automata 5700 you'll get the most formal definition. At least if I teach it, you will. So I'm going to call class P, my definition, class P is the set of all decision problems that can be solved from scratch in polynomial time. Class P is the class of decision problems solvable, and just for the sake of clarity, I'm going to include from scratch, right, with no additional information about the problem or the solution. So from scratch. In polynomial time. Okay, what do we mean by polynomial time? Well, there's a number of ways of writing this down. One way would be to say it's the union of all polynomial complexity class decision problems. Another way to say it is that we can use an algorithm that operates in big O of n to the k for some k. Okay, so let's say using an algorithm in big O of n to the k for some k less than infinity, some finite k. Okay, so so if a problem is in class P, then what that means is that there is a polynomial time algorithm, right, which solves that problem. Okay, so what we could do, just for starters. Oh, and by the way, we use the word tractable to describe problems that are in class P. So here, let's just give you another definition. If a problem is in P, we call it tractable. Okay, that's what tractable means in the context of this class. Is it means there exists a polynomial time algorithm which solves that problem. Okay, that's the definition of tractable. Okay, so let's look at problem 1 and say, is problem 1 in P, right? So what is problem 1? Well, it's this problem that says, given an array and a threshold, is there something in that array greater than or equal to the threshold? So the question here is problem 1, as defined above, in P? And let me just make sure that is super clear, right? So that's the membership symbol. Is it in P? And the answer is yes. How do we identify that the answer is yes? Well, we write down a polynomial time algorithm for solving the problem. So the answer is yes. The proof is writing down a polynomial time algorithm that solves the problem, that identifies whether a given instance of the problem is a yes instance or a no instance. So the proof is a polynomial time algorithm, and I'll just call this polytime algorithm for prob 1. Okay, and I'm just going to informally say what the algorithm is. You walk down the array, and if you walk all the way to the end of the array and you find nothing that's larger than m, then you return no. However, if you find something greater than or equal to m at some point along the array, you return yes. Right? That's an algorithm for identifying whether an instance of the problem is a yes instance or a no instance. So a polynomial time algorithm for problem 1 is walk down the array, if no element is greater than m, return no. This is the sloppiest, most informal pseudocode you'll see. Return no. Else return yes. Okay, there we go. There's a polynomial time algorithm for this problem. The polynomial, by the way, if you're thinking about polynomial in terms of trying to identify the degree of the polynomial, the degree of this polynomial is 1, right? This is a linear time algorithm. If you double the array length, then it could take up to twice as long to identify, whether or not, like to be certain about the answer to the problem. Okay, so this is P, the class of all decision problems that have polynomial time algorithms for solving them from scratch. Okay, so anytime I say P, I'm going to be very pedantic about being sure that I mean a decision problem, right? So if a problem is in P, then it has either a yes or a no answer. So one of the things this means is that the sorting problem is not in P. Okay, the sorting problem returns an entire array. So that means it is not a decision problem, even though it has polynomial time algorithms for solving it. Okay, so this is it's a distinction that's a little bit annoying, but it's an important one for making sure that we're all on the same page moving forward. P only includes decision problems. And that's not to say that there aren't other problems that have polynomial time algorithms. It just means that when we're talking about the class P, all we're looking at is decision problems, such as the one that I defined above, this prob1 algorithm or problem.